Welcome to the Deep Dive. This is where we tackle dense technical source material, pull out the critical findings, and basically give you the knowledge you need fast. Today we're strapping in, heading into material science. We're looking at structural integrity and that endless engineering puzzle. How do you make things light, strong, and reliably safe?
It's the absolute classic trade-off in design, isn't it?
Yeah.
Especially for really high-stress applications. Think rockets, maybe racing cars. You want the least possible mass, but you also need absolute certainty that your part won't fail, even if it has some tiny defect. And that certainty, well, it really comes down to understanding how a material breaks, and maybe more importantly, when it's going to break.
Okay, so our mission today is a deep dive into a specific technical paper. It's looking at a pretty cutting-edge blend, an aluminum hybrid composite. We're aiming to pull out the practical knowledge about this material, AL6061 CISTI cenosphere, and really zero in on this one surprisingly critical factor that decides how well it resists cracks. And that factor is the thickness of the part itself.
Seems simple, but yeah.
So let's start with the basics. What's the foundation here? Aluminum 6061 or AL6061.
Right. AL6061 is like the workhorse of the metal world.
Yeah. Super
popular, lightweight alloy. You see it everywhere because it's got this great balance of strength, corrosion resistance. It welds well. It's reliable stuff. But, to really make it a superstar for demanding structures, it needs a boost.
And that's where the hybrid part comes in.
Exactly. That's the hybrid part.
They use two different reinforcements to get this better performance. First up, silicon carbide, CNs.
CNC is the muscle, basically. It's incredibly hard, very stiff. It gives the material vital wear resistance, high thermal stability, too. It dramatically boosts the alloy's ability to carry load.
Okay, makes sense. And the second bit, this seems key for the lightweight goal. Cenospheres. For anyone not familiar, what exactly are these? Tiny, hollow, ceramic microspheres.
That's it, precisely. They're essentially microscopic hollow bubbles. Adding them is how you strategically, cut down the density of the final composite. You get a bonus. They add insulation properties, too. So the goal is synergy, right?
Synergy? Yeah.
You want the stiffness from the Sikia, the low weight from the cenospheres, and it's all held together by that AL6061 matrix.
But I imagine mixing these things creates a huge testing challenge. You mentioned fracture toughness, FT. Before an engineer signs off on this for, say, a plain part, they need a rock-solid, reliable FT value. That's the material's tolerance for a crack that's already there.
Exactly, and that reliability just goes out the window if your test doesn't mimic the real-world constraint on the crack. So the central challenge in this paper is proving that the test results they get aren't just, an artifact of the sample size they used. Because when you test a material, the thickness of that sample actually changes how the stress is distributed right at the tip of the crack.
Wait, hang on. Why does thickness change the stress distribution? Why can't I just test a thin sheet and, call it a day?
Okay, think of it like this. Imagine bending a really thin piece of plastic, like from a food container. It stretches quite a bit, it deforms, it fails pretty slowly in a ductile way. That stretching is happening in 3 dimensions. It's not very constrained.
Right.
Now, imagine trying to break a really thick, heavy steel rod.
Yeah, different story.
It just snaps, right? Very little stretching. That thick rod is under high constraint. It means the stresses are forced mainly in one direction. The plane of the crack now, they can't easily relieve themselves by deforming sideways.
Okay. So maximum constraint, like in a really thick sample, that's where you find the material's minimum toughness, its most brittle breaking point.
Precisely. And that maximum constraint condition has a name, plane strain. If your test specimen is too thin, you're absolutely measuring a kind of mixed failure mode, part ductile, part brittle. And the result you get, which they call conditional fracture toughness, KKK, is sort of inflated. It's unreliable for design. What we really want, what engineers need, is that reliable minimum value, the plane strain fracture toughness, or CATIA.
Okay, got it. This is a real deal. So how did they actually make this tricky hybrid material? You've got light aluminum, dense Siri, and these hollow cenospheres. Sounds like they'd want to separate.
Yeah, it's not trivial. They used a method called stir casting. So they melt the AL6061 base aluminum. Then they introduce the reinforcement particles, the CSE and the cenospheres. But crucially, they first meticulously preheated both types of particles.
Preheated to what?
To 350 degrees Celsius for about an hour before adding them to the molten aluminum.
Okay, that specific step, preheating it, often gets glossed over in summaries. Why is that such a necessary engineering hurdle? Why bother?
Oh, it's absolutely vital. It's all about interfacial bonding. If those little particles have any moisture, absorbed gas, maybe even oils on their surface, they stop the aluminum from properly bonding to the ceramic surfaces. That leads to gaps, porosity, weak points, basically ruins the composite. Preheating cleans and kind of activates the surface. It ensures that when they do the mechanical stirring, about 500 RPM, they get good, even dispersion before they cast the metal.
Right, avoids clumps and weak spots. So, okay, the recipe. They kept the CNS constant at 3 weight% seams. That's known to give good stiffness. And then they varied the cenosphere content to play with lightness and toughness. 3 W2%, 6 W2%, and 9 W2%.
Correct.
Now, the obvious thought, if you want the lightest possible structure, is just cram in as many of those lightweight cenospheres as you can, right? Go for the 9 W2%.
That's the logical push, definitely. But here's our first really big aha moment from the study. It underlines that material science is so often about finding a careful balance, not just maxing out one ingredient. The scanning electron microscope, the CM images told the real story, the microstructure.
And what did the CM show? What was the difference?
Well, the 3 WP% and 6 WD% cenosphere samples look great. Fantastic particle dispersion, really strong bonds look like between the aluminum matrix and the reinforcements. Yeah. But the 9 WT% loading, it showed significant agglomeration.
Agglomeration, so clumping.
Exactly. The particles just clump together into these big, useless masses within the aluminum. And these clumps, they instantly create huge stress concentration points. They introduce porosity. It just destroys the mechanical properties you were hoping for.
Wow. So that's a fundamental limit. The ingredient itself is great, but the manufacturing process, stir casting in this case, just can't handle too much of it without problems. Did the paper suggest any ways around that clumping, like different mixing speeds or maybe coating the particles, or was just finding the limit the main point here?
For this study, identifying that limit was the immediate goal. They confirmed that, yes, higher loading leads to failure through agglomeration, at least with this specific stir casting setup. For you listening, the takeaway is pretty clear. Chasing that extra bit of density reduction isn't worth it if you end up sacrificing the microstructure.
Makes sense. Okay, so they had these 3 composite recipes. Now they needed to find that magic thickness threshold for reliable testing. How did they do the standardized tests?
They followed the ASTM E399 standard very strictly. They used carefully machined samples called compact tension, or CT specimens, and they systematically varied the ratio of the specimen's thickness, which they call $, relative to its width, $. That's the BW ratio. They tested it across a range from 0.2, quite thin, up to 0.7, which is pretty chunky.
And the test itself involves making a tiny crack and then pulling the sample apart.
That's the gist, yeah. First, you use a special machine, a servo-hydraulic fatigue machine, to create a fatigue pre-crack. This gives you a very controlled, sharp, consistent crack tip, simulating a real-world flaw. Then you apply what's called monotonic loading. Basically a slow, steady pull until it breaks. You measure the critical load, PQQ$, and use that to calculate the conditional fracture toughness, TQQ.
Right, and this brings us to maybe the most critical finding in the paper, the bit that translates directly into engineering design, into safety. What happened when they plotted that toughness, KQ$, against the thickness, the BW ratio?
Yeah, this is the core result. They found a really definitive trend, and it was the same for all 3 compositions. The measured conditional fracture toughness, KQ$, it initially decreased, quite steeply actually, as the BW ratio, the thickness, increased.
Okay, so that proves the thinner samples were giving that artificially high toughness you mentioned, the mixed mode stuff.
Exactly. It confirms those thinner samples weren't under full constraint.
And then came the plateau, the money shot, as you might say.
The plateau is everything. That's absolutely right. Once that BW ratio hit a value of 0.5 or greater, the fracture toughness value just leveled off. It stabilized, became constant. And based on the specific dimensions they used, the stabilization point happened when the sample thickness got above 12.7 millimeters, or half an inch.
So why is hitting that plateau the definition of reliable data? Why is that constant value the one we trust?
Because that stable minimum value is the plane strain fracture toughness. That's the real material property under maximum constraint. This value represents the material failing in its most constrained, most brittle state, which means its lowest toughness state. And when you're designing something safety critical, like an aircraft part, you absolutely must use this conservative lowest K value. It guarantees the structure can handle the worst case scenario.
But they had to prove it was truly plane strain, right? Not just assume.
Oh, absolutely. Mm-hmm. The researchers didn't just stop at the plateau. The ASTM E399 standard is very strict. It demands proof that the failure really happened under plane-strained conditions. This involves checking a kind of complex requirement. The thickness, $, has to be greater than 2.5 times the square of the ratio of kink Willdale to the material's yield stress.
Okay, let's let's translate that formula into something practical. What does passing that mathematical check actually confirm for an engineer using this data?
It confirms that the sample geometry was big enough to contain all the plastic deformation happening right at the crack tip. In sort of plain language, it proves the metal wasn't able to stretch and deform its way out of trouble laterally. The thickness was sufficient to force that brittle, highly constrained failure mode. So when they confirmed the standard was met for the samples with a BW ratio of 0.5 and higher, they validated it. They proved that the measured KQ-TIRA value they got was a true, reliable KI2.
Okay, so this is the practical design rule coming out of the research. If you're making a structural part out of this specific hybrid aluminum, you absolutely must make sure its thickness to width ratio, BW, is 0.5 or more. Only then can you confidently use the calculated KI value in your safety calculations. That's really actionable knowledge.
Precisely. It gives designers a clear geometric target.
Now we know how thick it needs to be for the data to be solid. Let's circle back to the recipe. At that reliable KI level, which composition actually performed best? The 3, 6, or 9 weight percent cenosphere?
Right. The winner, in terms of toughness, was the AL6061, with 3W% CCC and 6WQ% cenosphere. That composite showed the highest stable fracture toughness. It reached up to 15.56 MPa square root meters. So that composition gave the best balance of achieving lightness and maintaining good resistance to cracking.
Okay, the 6% wins. Let's dig into why that was the sweet spot. What did the fractured surfaces show under the microscope?
Yeah, analyzing the fractography, the study of the fracture surfaces with EFEM was key here. It showed the main failure mechanism, for all of them really, was particle debonding, the aluminum matrix pulling away from the reinforcement particles.
Okay.
But in the poorer performers, the reasons for that debonding, or how it happened, were different. For the 3W cenosphere composite, the one with the lowest toughness, there were just too few particles acting as barriers. Microcracks could form easily in the aluminum matrix and just zip right through, relatively unimpeded. Low FT.
And the 6WT%, what made that one special?
The 6W% composite hit that sweet spot because the C-STEC and cenosphere particles were really well distributed. They acted as highly effective physical barriers. They literally forced the growing crack path to keep changing direction, to deviate around them. That takes more energy. It also helps redistribute the stress concentration at the crack tip, delaying the final fracture.
More crack deflection, higher toughness. Got it. And the 9WD% sample, the one that performed poorly, that just failed because of those internal flaws, the clumping we talked about.
Precisely. Those large particle agglomerates acted like big pre-existing defects. As soon as you put load on it, they initiated multiple cracks almost instantly. It's a textbook example, really, of how internal manufacturing flaws can completely compromise what looks like an excellent material composition on paper.
It's really impressive, though, that they didn't just rely on physical testing. They backed it up with computational analysis, too.
Absolutely. Good practice. The researchers performed 3D finite element analysis, FEA, using ANSYS software. They used it to simulate the stress intensity factor, the SEF, at the crack tip. And the results from the simulation lined up remarkably well with the actual experimental data. They reported percentage errors generally below plus or minus 10%.
Wow, that's pretty close agreement.
It is. That convergence between the lab results and the computer modeling really affirms that their predictive model is robust. It means design engineers can likely use this model with some confidence.
Okay, this deep dive has given us some extremely specific takeaways. Let's try to distill the critical knowledge for you, the listener. We found 2 crucial rules if you're designing with this specific AL6061 cenosphere composite. First, and this is huge for safety critical parts, you can only really trust the fracture toughness data if the part is thick enough. You must ensure the component meets or exceeds that BW ratio of 0.5. That guarantees you're using the true, worst case, plane strain Guy value in your engineering calculations. No inflated numbers. That's
rule number 1. And second, the optimal recipe, the best balance for high toughness and good lightweight properties, is the blend with 3W2% sine C and 6W% cenosphere. Pushing the cenosphere content higher to 9W2% is actually counterproductive. You sacrifice strength because of that destructive particle clumping during manufacturing, and you don't gain that much more lightness. 6% is the sweet spot they found.
So BW equals 0.5 and 6% cenospheres.
Yep. And if we zoom out a bit, look at the bigger picture, this work serves as a kind of template for developing and validating other hybrid materials in the future. It provides accurate, experimentally validated predictive tools for fracture behavior. And that's essential if we want to increase reliability in really sensitive applications, like, say, aviation structures. They've essentially given the engineering community a blueprint that connects reliable physical testing directly to advanced modeling.
Yeah, it really reminds us that structural performance isn't just about the percentages of ingredients you write down, not just the recipe on paper. It's about the messy reality of the microstructure, how those particles actually arrange themselves when you mix them up, and how they behave under stress.
Exactly. The research hammered home that controlling particle dispersion is just as critical, maybe even more critical sometimes, than the material's overall weight or the exact composition percentages alone.
Fascinating stuff.
So building on that, here's a final provocative thought for you to maybe explore further. If manufacturing limits, like this particle clumping issue, can completely negate the theoretical benefits of what looks like a perfect material recipe on paper, how much of today's cutting-edge material development is actually bottlenecked, not by discovering new amazing materials, but simply by the practical constraints of mixing, synthesizing, and manufacturing them at an industrial scale? What other hidden microstructural factors might be holding back the next generation of high-tech materials?